let's read that question again for number 12. So ABCD, oh, sorry. About that. ABC is a triangle with side AB equals to 10, AC equals to 14, and B side BC equals to 16. Point P is chosen uniformly inside triangle ABC. What is the probability that PA is less than PB and PA is less than PP? So I guess for this problem, there was I think you still have to know some definitions to solve this problem. There's like two definitions to solve it, right? So one of them, I think some of you already heard of this already, which is about perpendicular bisectors. So let's define first, or see what happens in a perpendicular bisector before we can solve the problem. So I guess in these type of problems, for this for perpendicular bisector, we know that this is 90 degrees here, and this bisects the side length here, the sides here. Let's say the endpoints are A, B, or we can just pick a random point here. So in perpendicular bisector, if a point is on the perpendicular bisector, let's say point Q, right? Then the distance from each of the points here are equal, right? How? Well, of course, that we can use Pythagorean theorem over here that these lengths are equal and these lengths are equal. Then we can use Pythagorean theorem or similarity of triangles to say that AQ is equal to BQ. But how about let's say if Q is not on the perpendicular section, right? Let's say it's closer to A. If it's closer to A, you can definitely see that BQ, length AQ is less than BQ. And this definition will help us to solve the problem so that we can find the probability with these type of conditions here. So now, that's one definition that we can use, that we will use for this problem. And another definition is, in a triangle, I will use the bottom triangle or bully growth triangle. I'm going to put this here. This way. In a triangle, the perfect the conquer all the perpendicular bisectors from AB, BC, and AC would concur at one point, which is called the circumcenter, which is we do not always cause, or most of the time, O, right? This means that the circumcenter O, if your point is on the circumcenter O, the distance here are all equal from each of the vertices, right? That's one definition that we will that we focus here. But we're not solely focused on like the circumstance itself, but how but with the definition we did here, okay, you find this. Okay, so we will apply with the why is that? Hold on. It's something over the inversion. Why is it on the call? Wait, my bad guys, I will be back. There's something wrong with the whiteboard right now. Is it back? Um, can you wait for a bit, guys? My mirror is lagging right now. I'm very sorry. Okay, it's back now. Okay. Okay. Very sorry, guys, for the delay. I'm very sorry. So again, we will have different type of definition. Two things that we have to use here: the definition of the perpendicular bisector and the figure of the circumcenter. Right. So now, let's try to draw. We'll use the second triangle at the bottom. We will try to draw like the circumcenter where it is. Not gonna be accurate, so sorry for that. So let's say this is circumcenter O, and let's say we have the midpoint here are D, E, and F. Right? So here's the main point of the problem. What should we do so that PA is the least likely, right? If you pick a point, random point here, I will do not put a speed here. Let's say, and I guess it's clear to see that um that we'll draw first some more lengths here on the starting center. It's clear to see that point P must be on these areas, right? Why is that? Well, let's say um a point P is not there, and let's say it's over here, right? Let's say point P over here. The thing is, this will make PA longer than PB because of our definition here. It's like um saying that because we know that OD, okay, OD is the perpendicular bisector. So if P is near to uh, if point P is near to B, then the length of P is gonna be smaller. So basically, this actually just finds us to solve for these areas, ADO and AFO, over the entire area of the triangle, which is of course probability of um, of ABC. So I think I will not go into deep with the computational stuff here because like there are multiple ways to solve for the areas here. You can try to, let's say, find for the circumradius of ABC with those given lengths, or you can try to just back with log cosines or whatsoever I did. I think that would be up to you, right? But um but the main part of this problem is to see how perpendicular bisectors here and about the circumcenter, how they work in a triangle. That's basically the main points for this problem. And eventually, you can try to do the theme of cosines, or try to bash to find the length chase, I guess, with the problems, with the problem with our lengths. Um, and you will eventually get the ADO, is equal to uh, 55 over 2 square 3 ASO is equal to um 49 uh 2 square root 2. And I will just give you a brief on how I got these areas real quick. What I did is try to solve, let's say, um, for this angle, which is like I try to solve for, let's say, this is 5, 8. I try to solve for this angle here, then try to um solve for the area of ABC. Then you could length bash it with just the definition is well defined angle ABC is equal to angle POS. Then you can try to solve for the other length. But one can also do to find the circumradius of the triangle. This one. Then try to solve for the areas and later on solve uh, for the areas of each triangle mentioned. So that's just like a brief case over there. If I try to maybe go on to it, I think it will waste time. So that's I'm very sorry for that. You can try to ask later on about these problem if you have questions later for this problem later. So eventually, um, going back here now, go here with triangle ABC. It's also 40 is 43. Using our probability here, we have to the probability of point P inside the point P. Oh no, sorry. Why am I defining that? Very sorry. That was stupid of me. I meant PA. Sorry. Very sorry for the probability part. So PA is the least here is equal to 55 over 3 square 3 plus 49 over 3 square 3 over 40 square root 3 can simplify this to 52 over square root 3 over 40 over square root 3. Can cancel here. This will multiply it with this. This will be 13, this will be 10. And eventually, you'll get into 13 over 30 is the answer. Equals to 8. So again, my explanation here is to show how we can try to simplify the problem further with the definition of the perpendicular bisector here and over here. And yeah, that's how you solve problem 12.